Okay, good morning, my dear modern geometry students. We shall now start discussing lesson 2 on finite projective planes of our module 1. So for this lesson, our objectives would be for you to be able to prove theorems pertaining to finite projective planes and discuss or defend your own proof. Okay, so in activity 1, you were asked to view or watch a video focusing on the constructible points. Okay, my point there is that you would be able to get an idea on what we meant by axiomatic systems. That would be one truth leads to another. Okay? So here, we are asked to read pages 9 to 18 of our textbook. So this topic would be quite long. So we shall have several videos, meaning this video lecture would be done in several parts. Okay? For today, we shall try to prove the first theorem of this topic. So, for us to understand what is a finite projective planes, we have here the axioms of the finite projective planes. We will be talking about point, line, and incident. Okay? Then we define points incident with the same line are said to be collinear. So these are lines which lie on the same line. Okay, collinear points. While lines incident with the same point are said to be concurrent. In other words, intersecting. So these are lines which contain a common point. So they are said to be concurrent. So for the axioms, axiom P.1, there exist at least 4 distinct points, no 3 of which are collinear. Meaning it would be safe to assume that there are at least 4 points. Meaning, for us just to get a vision, so we shall have 4 points. No 3 are collinear. So let us call this point P1. This point P2. Let us call this point P3. Or let us just change the color of the labels. Okay, for distinction. So call this point P1, this is point P2, this is point P3, this is point P4. Next, we have the axiom there exists at least one line with exactly n plus 1, where n is greater than 1, distinct points incident with it. Okay? So at this point, this would be quite ambiguous because n here is an arbitrary integer greater than 1. What is meant to say here is that if n is 2, so there would be exactly one line with exactly 3 points on it. If n is 3, so we say that there exists at least one line with exactly 4 points on it. Okay, so we'll just go back at that axiom later on. Let us just focus on axiom P.1, axiom P.3, and P.4. Axiom P.3 states that given 2 distinct points, there is exactly one line incident with both of them. For every pair of points, there is exactly one line. So if we would go back to our illustration here, let us color the lines blue. So for P sub 1 and P sub 2, there would be one line containing both of them. Let us call it L sub 1. P3 and P4 would be contained by exactly one line also. Call it L2. Then there would be a line containing P1 and P3. There. Call it L3. There would be another line containing P2 and P4. Call it L4. There would be a line containing P1 and P4. Call it L5. Let us transfer the label for L2. So this here is L2. Then there would also be a line containing P2 and P3. Let us call this L6. Okay, so although it looks like L5 and L6 intersect, but they do not necessarily intersect. Okay, this is just for illustration purposes. Take note that there is no point. It is not necessary that there is a point containing both, which is contained by both L5 and L6. Okay, so again, this here is the point P4. This is point P1, this is point P2, and this is point P3. Next. In the next axiom stated that given two distinct lines, there is at least one point incident with both of them. At least one point, common point between two pairs of lines. So we see here that L1 and L2 has P3. L1 okay. L1 and L2 must meet in some common point, okay, somewhere here, but not on any of these 2 points, any of these 4 points here, okay, because that would violate the first axiom. So L2 and L1 must meet somewhere here or somewhere here, but here we have L1 and L3 meet at P1 rather. L1 and L4 meet at P4, and so on. Okay. Just be reminded that every two distinct lines must meet at least one point. Now, we have here some models that would help us understand how this axiomatic system works. Here are 3 models. In model P1 and P2, each line has 3 points. Okay, actually model P1 and P2 are just isomorphic. Okay, just change the name of the points from A to G to the dots named 1 to 7. Then the segments are illustrated or represented by columns in model P.1. Okay? Here is a model wherein each line has 4 points here. Okay? Now, this would mean that a finite projective plane, a model for finite projective plane may have 3 or 4 or maybe more points, but it would be impractical to do trial and error to find out what integers n for which a finite projective plane would exist. Okay? It would be wise just to prove theorems, conjectures, basing on the four axioms of the finite projective planes instead of doing trial and error to find out what number of points are there in a finite projective plane, the maximum number of points. Okay, let us now define what the principle of duality means. An axiomatic system in which the dual of any theorem is also a theorem is said to satisfy the principle of duality. Meaning, here we have, if we go back to the axioms of the finite projective planes, we have four axioms. If all four axioms of, if the dual of all four axioms in this system are theorems, meaning can be proven true, that would mean that the finite projective planes is an axiomatic system which satisfies the principle of duality. We can actually prove that by proving the dual of each of these four axioms. Okay, so here we have the dual of axiom P.1. Recall that when we say dual, we simply interchange the words lines and points, and consequently we would also interchange the words or the terms incident and collinear and concurrent. When we talk about points, we say collinear, but points in its dual becomes lines, so these lines would be concurrent instead of collinear. Okay, and vice versa. So go back to the statement of theorem P.1, which is actually the dual of axiom P.1. So it states that there exist at least four distinct lines, no three of which are concurrent. Okay, so recall that axiom P.1 states that there exist at least 4 points, no three of which are collinear. So its dual would be there are at least 4 lines, no three of which are concurrent. Let us try to prove that. Okay, take note that we will just use these axioms, the 4 axioms of the finite projective plane. We shall try to prove this using the proof by contradiction. So suppose that it is not true. Okay, suppose it is not true that there exist at least 4 distinct lines no 3 of which are concurrent. This is equivalent as to saying that for any 3 lines there is at least one point incident with all of them, because it is the same as saying that there are no three lines which are for every four lines rather. Okay, let me check this. At least four lines, distinct lines, no three of which are concurrent. For any four lines, there are at least three which are concurrent. Okay? Because it means to say that it is impossible for four lines in which no three intersect at a single point. This is what the negation of the theorem means. So if we would go back to axiom P.4, by axiom P.4, let's go back to P.4 first. Okay. What does P.4 state? That given two distinct lines, there is at least one point incident. But first, let us consider P.1 saying that there are at least four distinct points, no three of which are collinear. So axiom P.1, there are at least 4 points, no three are collinear. Meaning, so again we have 4 points here just to help us think. Okay. So again, these are points P1, P2, P3, and P4. Okay? Let us just include the names of the points in our formal proof. Say P1, P2, P3, and P4. Okay. It is important to note that these 4 points are distinct, at least 4 distinct points. Meaning, P1 cannot be the same as P2, nor P3, nor P4. P2 cannot be P3, nor P4, and P3 cannot be P4. Okay? They are pairwise distinct, or each is different from the rest or the other three. And also, no one line can contain three of them. Okay? There is no one line that can contain three of them. Meaning, if a line contains P1 and P2, it cannot contain the other two rather. So, if there is a line here, and it contains P1 and P2, it should not contain P3 and P4. Let's call this again L1. And then by one of the axioms also state that for every two distinct points there is exactly one line. So every pair of points is contained by exactly one line. So there must be a line also that contains P3 and P4. Again, let us call this L2. There is also a line containing P3. P3 and P1. Let us call it L3 again. And a line containing P2 and P4. We say line in this context. It's not necessarily straight. Okay, for as long as these are just representations. An idea wherein a set contains 2 points P2 and P4. So there is also a line that contains P1 and P4. Let's call this L5. And a line that contains P3 and P2. Let's call it L6. So we say that by axiom P point 3 there is a line L1 that contains P1 and P2. Similarly, there is a line containing P3. There is a line L2 containing P3 and P4. In the same manner, there are lines L3 to L6. containing the other pairs of points. Okay? So this would mean that L1, let me continue now this time by writing on the board, the whiteboard. Okay? So here, this would mean that by the way, it should be stressed here that we came up with 6 as the least number of lines because if we take a pair of points from 4 distinct points, we simply count the number of combinations of 4 taken 2 at a time. Okay? So that would again give us at least 6 lines. Okay, so this would mean that here, since L1 contains P1 and P2, okay, take note, P1 and P2 are on L1, would imply that P3 and P4 cannot be on L1. Otherwise, there would be through 3 points collinear. Okay? In the same sense, in the same manner, we can say that since P3 and P4, sorry, are on L2, this would mean that the other two, P1 and P2, cannot be on L2 anymore, and so on. Okay? Meaning only two of the 4 points P1 to P4 can be contained on a line L1 to L6. Also, we should see that, let's make it thinner. We should see that since P1, so we say also P1 is in L1 and P1 is not in L2, would go to show that L1 is not L2. Okay, so as we see here, here is P1, it's contained in L1, and here is L2, not containing P1, meaning L1 is different from L2. Also, P1 is contained in L1, but it is not in L4, which means that L1 is different from L4. Also, we see that P2 is contained in L1, but it is not in L3. So P2 is in L1, but P2 is not in L3, which means L1 is not L3. Okay, when we can do this pairwise, there would be what? 6 taken 2 number of these pairs, and it would go to show that no two lines are the same. So this would mean that each line is distinct. So we are talking here of L1 to L6, okay? Distinct. So there are at least 6 distinct lines in our in this context. Now, let us go back to the assumption. The assumption states that for any 4 lines, there are at least 3 of which are concurrent. Okay? For every 4 lines. So, say we consider the lines L1, L2, L3, and L4. The assumption should imply that at least 3 of them must be concurrent. There are 3 of them that contains a common point. In other words, so we can just say without loss of generality suppose L1, L2, and L3 are concurrent, because there are always 3 of these 2 based on the assumption. There are always 3 of these 4 which are concurrent. So let us just assume that the 3 that we meant to be concurrent are L1, L2, and L3. So we can say that that is L1, L2, and L3 has a common point. They intersect at a point. Let's call it P. Now, note that in our earlier statements, okay, let us now focus on these 3 lines. Let us make another drawing here below where only these 3 lines are involved. So we have here L1 based on our drawing. L1. This here is L2. This here is L3. Also, based on our assumption, we have here a point. This here is a point. This here is a point. We call this P1. We call this P3. Now, note that P1 is on L1, but P1 is not on L2. So this would imply that P1 is not P. Why? Because P should be on L2, because it is a common point. It is common among L1, L2, and L3. So P1 cannot be this point P. Also, P3 is on, we look at the figure, P3 is on L2, but P3 is not on L. it's not on L1. So this should imply that P3 cannot be this point P that we say is common to all three of them. So there must be another point. There should be another point P. Here. Other than P1 or P3. So here is P. Now, note that since P3 is different from P, so these are two distinct points. So by one of the axioms, that is axiom, what axiom is that? Sorry. Axiom P.3. Every two distinct points is contained by exactly one line. So we see here that P3 and P are distinct. So by axiom, P.3, there is a line. A line, let's say L, different from, or not necessarily different. We'll show that it is different. For as long as it contains both P3 and P. Containing P and P3. But note that P is in L3 and also P3 is also in L3. So by axiom P.3, every pair of points can be contained by an exactly one line. So there should be only one line that contains both P and P3. It contains L. They are contained in L, and they are also contained in L3. So that should mean that L is L3. L must be the same as L3. Also take note that L2 also contains P3. P3 is also contained in L2, and since P is common to L1, L2, and L3, P should also be in L2. So again, this would mean that L is the same as L2. Now we see here that L is L3 and L is L2. So that would mean that L2 is the same as L3, which contradicts the findings earlier that L1 through L6 are distinct lines. So we say which is a contradiction to the fact that L2 and L3 are distinct. Hence, our assumption cannot be true. What assumption is that? That for every 4 lines there should be 3 that are concurring. Meaning there should be, we can always find 4 lines such that 3 of these are not concurrent. That is, there are at least 4 lines, no 3 of which are concurrent. Which proves the dual of axiom P.1. Okay, so we'll just stop there, and we shall continue with our discussion of this lesson in our next video. Okay, see you. Bye.